Professor Kim. Yesterday we have know about uh, for today we will listen to a lecture about the introduction to semi-supervised domain adaptation. So before the lecture from Professor K, we will firstly hear an introduction from Professor Benjamin Kusmoputro about our lecturer today, and Professor Kim will have a lecture around 80 minutes. Before after that, we will have a Q&A session and a photo session. So Professor Benjamin, the time is yours.
Okay, ladies and gentlemen, graduate and undergraduate students and all of the audience. Today we can have an honor to invite Professor Chang-Ick from KAIST to deliver the recent research in the field of computational intelligence. I would like to thank to Professor Kim for the last lecture last week. We have about 120 attendants, and many of them have requested the lecture video, and there are many of them that will participate in this lecture also. We are hoping that this consecutive lecture will open up a new direction of research, especially in the University of Indonesia, and we are very eager to listen to the lecture today. So please give a big applause to Professor Kim, and we would like to hear this lecture.
Thank you.
Thank you.
So, okay. I can share. Can you make me active? I cannot share my presentation. Okay. 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 It's weird. How can I? Okay. So, okay. Everything okay now? Do you hear me?
Yes, all good, Professor Kim, all good.
Okay, everything good, right?
Yep.
Okay,
Yes.
so let me start here. Okay.
Yes.
Good afternoon, everybody. Thank you again for inviting me, and it's my pleasure, especially my pleasure to Professor Benjamin and Professor Subiantro. Okay. Last week we discussed future learning and future officer recognition, and I want to say again these areas are very promising because most of our applications are developed under the conventional supervised learning setting can be reconsidered under the future settings. Okay, so today's topic is semi-supervised domain adaptation. I'll start with some basic. So I'll start with transfer learning and domain adaptation, the concept of transfer learning and domain adaptation. And we will talk about unsupervised domain adaptation, which has been most popularly studied among various domain adaptation settings. Finally, we will talk about semi-supervised domain adaptation, and then I wrap up my presentation. So as everyone knows, machine learning comes in various forms, as you can see here: supervised learning and semi-supervised and unsupervised learning and reinforcement learning. Okay, last decade, supervised learning was very popularly studied, basically yielding very good results, especially on computer vision area and speech recognition. However, supervised learning is only applicable where there's enough quality data, and the data can capture the entirety of possible scenarios. So as soon as trained deep learning models face unfamiliar examples that differ from their training examples, they start to behave in unpredictable ways. So according to many experts, it is necessary to develop AI systems that learn with fewer samples or fewer trials. To this end, the suggestion is to use semi-supervised learning or unsupervised learning. And our today's topic, the domain adaptation, which is also in the same category as transfer learning, that is located between supervised learning and semi-supervised learning. Okay, so it is it begins to draw attentions last just 3 or 4 years and keep growing. And that is our main topic today: domain adaptation and transfer learning. And by the way, I hope you don't you are not misled by this figure. Uh, Actually, domain adaptation or transfer learning cannot be parallelly compared with supervised learning or supervised learning, because inside transfer learning or inside domain adaptation, we also have supervised domain adaptation, semi-supervised domain adaptation, and unsupervised domain adaptation. It's similar. Similarly, in reinforcement learning, there are supervised reinforcement learning and so on. Okay, so don't be misled about from this uh, picture. And just this is just a beginner level slide, just to recall the supervised in the supervised setting. All the data is labeled and the algorithms learn to predict output from the input data. Okay, so there is a labels as well as input data. So supervised learning, the main subject is classification or regression. In the case of unsupervised learning, all the data is unlabeled. So the algorithm should do by himself something. So like as you can see in the picture, we can do clustering or dimension reduction, just according to the feature distributions. Okay. And semi-supervised learning cases, some data are labeled only, but others are all unlabeled, as you can see in the picture here. So it's just the middle, it's located in the middle of supervised learning and unsupervised learning. What we can easily consider is to make label propagated. For example, here, if we look at only labeled samples, then maybe you will agree to have just a horizontal boundary. But if we look at the even unlabeled data altogether, then the horizontal boundary is not appropriate, right? But then how can we do? Just what we can do first is to propagate a label, like since the next one is very close to the black one, this one is labeled as black, and keep just going. Okay, so that is how we propagate. So in other words, we can say that we use a geodesic distance rather than a Euclidean distance. In terms of Euclidean distance, actually, this one is closer to the black point rather than this one. But all of you will agree with this kind of categorization, because they can be grouped all together, just nearby. They are all linked nearby, right? So that is how we usually do label propagation. And the keyword is geodesic distance rather than using Euclidean distance. It's similar one, but that's not our topic. So just in terms of mathematics, just we think about, we consider the case that we have input data with along with labels, and also we have unlabeled data. But in this case, the number n is much bigger than the number of errors. So that means we have much more unlabeled data. Okay, but we also have some labeled data. That is a well-known semi-supervised learning scheme, as you know. And in other words, semi-supervised learning is to learn from unlabeled data, right? So we don't just throw unlabeled data just away. We just try to use, we try to learn something from unlabeled data. In the case of transfer learning, we try to learn from data in other domain. Okay, that is the basic definition of transfer learning. Examples are here, as you can see in the left side. We have 4 different objects in the left picture with a white background. And on the next figure, we have the same category objects with a different backgrounds. That's the difference. So if your deep learning model is well trained on the data in the left side, maybe that model will not be successful to deal with this one with different background. So we say that even though their categories are same, the domains are different. Okay, that is one example of transfer learning, and even the categories can be different as well. As you can see in the right side, there are, in this case, we may say the domains are same because their colors, their image feeling, they are very similar. So domains may be similar, but in this case, categories are different. So I prepared this table that there will be, of course, 4 different cases. The first one is source domain, target domain, they are same. And tasks are same. By task, at this moment, we can say that the categories are same. Like this one, left one, tasks are same. They have 4 categories, same 4 categories in both domains. So tasks are same, domains are same. So that is nothing but a conventional supervised learning, right? Because we don't have to think about the different domains. They are actually one domain because both domains are same. So one domain, one task that can be solved by traditional supervised learning. The second one is the case where the domains are same. So actually one domain with different tasks. It can be viewed as multitasking. Okay, and multitasking is also categorized into inductive transfer learning. The third one is actually our main topic today. We have 2 different domains and tasks are same. As you can see again here, 2 different domains with same task. Okay, that is also categorized in the transfer learning, but specifically just this third line is specifically called domain adaptation. And also the fourth one, both domains are different and tasks may be different. That is called transfer learning. So in the narrow viewpoint, the second one is multitasking. The third one is domain adaptation. The fourth line corresponds to transfer learning. And the more broad perspective view, we can say that the bottom 3, they are all in the category of transfer learning. So transfer learning is can be viewed as a bigger concept that include the domain adaptation. or just a narrow viewpoint, the fourth one can be categorized into transfer learning. But usually the transfer learning is a bigger concept. But when you think about domain adaptation in the third line, both domains are different, but tasks are same. That means even though we have two different domains, if in the target domain we have also a bunch, if we have a bunch of labeled data, then no one wants to use just the source domain data. I can do my deep learning with the target domains with labeled data, so it becomes nothing. So we also think about this constraint. In the target domain, nothing is labeled. So in the case of, in conclusion, in the case of domain adaptation, we have two different domains and the tasks are same, but in the case of target domain, they are not labeled. Only the source domains, they are labeled. This is monitor, this is helmet, this is a cup, this is a keyboard. But in the target domain, they are not labeled, but the domains are different. But categories are same. That is a definition of domain adaptation. This one just shows traditional deep learning case. According to your task, you have to build your deep learning model accordingly. But transfer learning, as the name says, we try to transfer knowledge which was obtained in the source domain task to the target domain task. So a little bit of mathematics here. So by domain, we mean it is composed of feature space X with the probability of P of X. And by task, we mean it includes label space Y with the conditional probability P over Y given X. If you don't understand what I mean, don't worry. I have a very easy example in the following slide. Similarly, anyway, at this moment, we can also put S and T to distinguish source domain and target domain. So similarly, domains are composed of the samples and their corresponding probabilities. And tasks are defined as a label space and their conditional probability. So if domains are same and tasks are same, okay, then that is just the conventional machine learning case. Okay, so we don't have to think about transfer learning. Actually, one domain, one task, right? But in the case of different domain or different tasks, then they are in the category of transfer learning. So specifically in the case of domain adaptation, that means different domains and same tasks, same tasks. So here's a specific example for domain adaptation. So here, the domain, in the case of domain adaptation, the domains are different. As you can see here, the backgrounds are so different. So maybe the well-trained in this domain may fail to deal with this domain. So domains are different, but tasks are same. By same task, we mean this one, label space is same. For example, here, labels are same. Label space include the helmet, monitor, cup, keyboard, but in the target domain also helmet, monitor, cup, keyboard. So label space are same. And also the conditional probability should be same. That is actually basic definition of domain adaptation. I have very easy example here. What does this mean? Label space same, that means there are same categories in both domains. what does mean by conditional probabilities are same? That means when we have source domain data given, okay, source data given, their probability, helmet is y1, helmet level is y1, monitor level is y2, cup level is y3, keyboard is y4, for example. Their probability is 0.3, 0.1, 0.4, 0.2. In the target domain, their conditional probability, when the samples are given, their probability of helmet is 0.3. Their probability of monitor is 0.1. So same, the probabilities are same. That is basic excuse me, basic definition of domain of adaptation. But some people may think about this. The label space are same. That is agreeable, but just the constraint for the same conditional probability is too harsh. How can we guarantee the probabilities are also same in both domains? So we relax the definition. So their probabilities may be different, but as far as label space are same, so that means there are same categories. As far as there are same categories in both domains, we just recognize it is the case of domain adaptation. So again, in conclusion, in this case, domains are different, but the level space are same. Even though conditional probabilities are different, we can say that it's just a domain adaptation setting. I hope everyone easily understand, right? And this one, I will keep often show the tables so that you can always recall. So in the case of domain adaptation, we can easily guess the unsupervised domain adaptation case. That means source domain samples are labeled. Okay, but as we saw here, no labels in the target domain. Okay, but in the case of semi-supervised learning, target domain, some labels are labeled. Only one or three shot labeled. Very few labeled. Few samples are labeled. But since it is a semi-supervised setting, we have also unlabeled data in the target domain. But in supervised domain adaptation case, we have target samples labeled, but the number of labeled samples is only one or three shots. Why we don't have a bunch of labeled target images? If you have a bunch of labeled target images, actually you don't need to have source domain data. Using bunch of target domain labeled data, you can use conventional deep learning. So always the number of shots, labeled shots are limited to one or three. And there, of course, there is no unlabeled target images in the case of supervised domain adaptation. Okay, it will be easy, and I will show you similar tables in the following slides sometimes. And whenever I say there are different domains, that means we can also say that there is a domain shift. Okay, so by domain shift we mean the background is different between domains, or location is different. Of course, the location difference will give you some background difference, and pose may be different. And more, the severe ones are like the difference in types, like one is photo, the other target domain ones are sketches, or one is just RGB images, target domain images are IR images, or paintings, or sketches. They are all domain different samples, right? So we say that there are domain shift. Okay. And what happens if domains are different? This is the case. There is no domain shift. Like in the training stage, we used some data set called the cityscape, and we tested with the images from the cityscape. So the result is pretty good, right? Everything seems to be okay. The categorized, very segmented, with very good performance. But if you train the data in the cityscape but test on the different benchmark, like San Francisco videos, then you will see uh, you, uh, your segmentation results are degraded. That's because domains are different, right? Because you trained in one domain, but you tested in the other domain. So since there's a domain shift, your algorithm doesn't give you good output. Even when you are in the tunnel, the your uh, the system will collapse much different, right? So that this one shows domain adaptation. When there's a domain difference, domain shift, your system is not working very well, will not work very well. So we have to what actually domain adaptation does is to align target domain with source domain. So we have the bottom one is a source domain. We have a source domain data, and they are well divided by this boundaries classifier. But we have target data without aligning. They maybe we may fail to divide them correctly. So before we have a classification, we better align those features together. So for example, when they are well aligned like this in the right side, and then we can use the classifier which was trained in the source domain. So as far as target domains features are well aligned with source domain features, the result will be very good compared to without alignment. So one other example is when there are well-known the number data, right? Digit data, MNIST and USPS. So when the MNIST is used in source domain, and also it is tested or in the target domain. So I mean, both source domain and target domains are same. The recognition performance is very high. Okay, whatever the source domain, target domain, as far as they are same. But if the source domain, target domain data are different, their accuracy dropped, right? So this one shows why we need to have a domain adaptation. So again, we see the same tables. Uh, in the source domain, whatever settings we have labeled data. But in the target domain, unsupervised domain adaptation case, the data samples are not labeled in the target domain. But in the semi-supervised domain adaptation, we have just a few number of unlabeled, small few number of labeled data with a bunch of unlabeled data. And supervised DA, we have labeled data in both sides. But labeled data in the target domain should be very small. Okay, in the case of supervised DA. So since unsupervised domain adaptation through the most of attention so far is better to think about to start with unsupervised domain adaptation. Again, by unsupervised domain adaptation, we mean there are source domain, labeled source domain data, but unlabeled target domain data. Okay, that's how we what we have now. Again, we have domain difference here, but source domain they are labeled, but in the target domain they are not labeled, but domains are all different. So we can use unsupervised domain adaptation. In the category of unsupervised domain adaptation, actually it's not just the concept itself is not just in the category of deep learning. Actually, before deep learning, we, many people also considered domain adaptation. So sample reweighting or subspace alignment, they are just unsupervised domain adaptation schemes before we have deep learning. But nowadays, we are just focusing on deep learning. So just the deep learning based unsupervised domain adaptation is very popular. So I will skip just schemes before deep learning era. Just I want to just start with deep learning based unsupervised domain adaptation. Okay, so there it can be divided into feature alignment based and also appearance based. Okay, I will explain them a little detail. The first one is divergence-based domain adaptation. It's very concept is very easy. There are two different the feature distributions because of different domain. Okay, because of domain shift. So there we use some kind of a divergence measure until two distributions become similar. Okay, so we can use several divergence measure that is used to measure the difference between two distributions. So until the distance between two distribution becomes very small, we keep just adjusting features. Okay, so among MMD, Corel, CSD, whatever, the mostly popularly used one was MMD, maximum mean discrepancy. So we measure mean of two distributions, the centroid of two distributions, and we measure the distance between two mean vectors. Okay, that is our measure for the MMD. Okay, so one easiest idea to align two different domain distribution is to build this kind of framework. So that their weight parameters are all shared. Okay, so everything in both domain, they are the parameters are shared so that they have a same mechanism, same weight parameters. Okay, then they will produce a very similar feature vectors we can easily expect. But in this paper, just presented in TPAMI 2019, they just relaxed this constraint by replacing the shared module with a loss module. So that means as far as they are linearly related, it's okay. That means images, for example, in the first layer, the the images in source data are very bright, but images in the target domain are a little darker. So they cannot be same, but they are always linearly related, right? So my pixel value times 2 minus 30 will be similar to source data, for example. So they are linearly related. They made that module. So there are 4 different loss functions. That means uh, the upper two are just for they are just standard classification laws. So from the source domain, from the target domain, there will be two standard softmax loss or cross entropy loss, that is cross entropy loss. And this one, regularization loss, is defined as this one, equation 6. That means that this one should be minimized. That means they are related to linear. They should, as far as they are linearly related. If if the, if we define the loss as the small difference between two parameters, maybe source vector minus, that should be source vector minus target vector. But here they just relax the constraint so that this source vector's linear relationship should be very similar to target representation. So they are linearly constrained. That is the this loss, regularization loss. And last one is to measure MMD. So when, as you can see here, if the feature vectors from the last layer, as far as they are same, when they are mapped into the RKHS space, some space called RKHS space. When they are mapped into RKHS space, their difference are very similar. Then we mean the two different distributions are now very similar. Okay, so this MMD loss is to make two distributions aligned. Okay, but as you can see in the sentence, they say that in practice, mapping into RKHS is not typically known. It's not known. So we usually, in practice, we use just Gaussian RBF kernel or Gaussian kernel. That means if the features are very nearby, located nearby, then according to Gaussian kernel, the kernel response is high. If the features are very far away each other, then according to the kernel response will be very small. So easily speaking, the features are similar. Uh, I'm sorry, the features are similar, then distance will be very smaller. Okay, so so the just we can just set the adjust so that if they are similar, the loss becomes very smaller. Okay, okay. But in terms of Gaussian, it is maximized. The distance are smaller, the Gaussian value will be maximized. In that case, we can also put a minus sign so that it can be smaller. So it is trivial, right? So maximized or minimized, that's not concern. Actually, it can be easily implemented. Okay. So by using this one, their goal is to align two different distributions. Okay, again, classification should be done very well, and both domains should be related linearly, and also their distribution should be very similar. Until their feature vectors are very similar, we keep training so that this MMD loss is minimized. Okay. Any question? Clear, right? Okay. Then the next one is just the most popularly used feature alignment technique. The most popularly used deep learning based domain adaptation, unsupervised domain adaptation technique. It's very clear. Its goal is to first, this one, upper one is source domain data, and bottom one is target domain data. As you can see, there are domain shift. One is from computer generated one, and bottom one is just a real picture. So domains are very uh, different. So anyway, and since note that record that we don't have labeled data in the target domain. So we cannot do any kind of supervised learning because there is no label. So for the source data, we do classification. Okay, we can train some classification. So we have to generate the features that is very good for the classification. At the same time, our generated features should be very similar, right? So that when we have real data in the test stage, they should be they can be classified correctly. So in order for this one should be classified correctly, that means is the this real pictures horse feature and computer generated horse feature should be very similar, right? Then it can be classified accordingly correctly. So that means in order to make generate similar feature vectors, we put discriminator. That is always that has very keen eyes to figure out uh, they are different. Oh no, this is from graphics. This is the real data. So they have very keen eyes. Because of this, they try to generate very good feature to deceive this discriminate. I have to deceive this discriminate. Okay, so that he cannot distinguish if the feature is from upper side or bottom side. Okay, our goal is to deceive the discriminator. At the same time, our another goal is to generate feature that can be classified very well. Okay, at this moment, I know most of you are thinking of GAN actually. Bro, the success of GAN, okay, that is to generate this is generative model, so its goal is to generate some unseen pictures, right? So in order to have a successful job, the 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 existence of policy, the discriminator is very important. So always, we explain again with this example, the counterfeiter and police. So let's say there is a counterfeiter that who wants to create counterfeit bills, which is a fake money. Okay, but without police, maybe there is no concern. So he will just make a copy of real of bills. Okay, and they don't need to worry because there is no police in the world. Okay, so their fake money quality will be very low because we don't have they don't care because there is no policy, no probability to get into jail. Okay, so if we are thinking about good quality of fake money, then the policy is very critical because if there's a police and with very keen eyes, then counterfeiter will try his best, right, to create a very real looking fake money. So always this is the discriminator is like a police or it is like a ordeal, very difficulty. Without difficulty, we don't try our best. But if there's a difficulty or ordeals or police, we try our best. That's how GAN was successful. So thanks to this kind of discriminator, it kept going. If the discriminator or police don't do their job very well, then their final picture may be like this. Ah, this is my fake face, but it's not that real looking, right? But thanks to the discriminator or the police, he they keep going. Then discriminate saying, oh no, this is still a fake. I know this is fake. Okay, so it's not real. So they keep doing until the discriminator or police agree with that. Oh, I think I'm confusing. I don't know where it is from. Okay, then we can stop and show the result. And now it is just indistinguishable, right? So that's how discriminator does. Returning to our adversarial approach. Okay, then by adversarial we mean there is a scheme inside there just adversarial modules are inside like policeman and counterfeiter, or there's some ordeals, there's some difficulty. We deliberately provide some difficulty so that they can do their best. Okay, in this case, the ordeal or difficulty or policeman is this discriminator. They all, thanks to, because of this discriminator, they they try to deceive this discriminator. So in order to deceive discriminator, they try to produce very similar, indistinguishable feature vectors from both sides. Why producing similar feature vectors is important? Because we don't have a labeled image in the target domain. So they should be going through this classification, this classifiers to get the result, test result. Okay, for the computer generated holes or real holes, their feature vectors should be very similar so that the is classification result is same as this classification. For this one, we can have classification result because in the source domain, we have source data and labels, corresponding labels. So as far as these ones features are very similar to horses label, then we can get the result. So again, sorry, discriminator try to distinguish from both sides. But here we try to deceive the discriminator. So finally, we will get very similar feature vectors from the same categories. And or at the same time, we can do classification very well. So using this idea, the very popular one is this paper called unsupervised domain adaptation by backpropagation, or we simply say just the GRL algorithm, GRL based algorithm, because gradient reversal was proposed. Again, they for the source domain images, they try to do their best for classification. And at the same time, this policeman or discriminator try to distinguish if it is from source data or source domain or target domain. So our goal is to produce our feature generator, try to generate a feature that is indistinguishable. We try to deceive this police, okay? But its goal is to distinguish. So in order to make the distinguished job very well, so we have some this discrimination laws. Okay, so to minimize and we make a back propagation. So if the back propagation is done correctly, the feature should be different from features from source domain, features from target domain. They should be different because in order to make this one satisfied. So in the layers for feature generation, their gradient is reversed so that they do opposite way. That means so that the features are similar. To help this discriminator, goal is to make features different, right, according to the domain. But by putting minus sign, putting making the gradient minus, that means they do the the features generate very similarly. Okay, so they do original backpropagation, but in the feature generation layers, they do oppositely, so that features are similar for the same category. That is how GRL mechanism is doing. Since this is very important in understanding unsupervised domain adaptation, just let's do just once more. So, for the source domain, since the source data are well labeled, they can go through this classification. The features should be well represented to be well classified. And this discriminator try to try to distinguish feature from source domain and feature from target domain. I have very keen eyes, so I can say if you are from source domain or target domain. So this feature extractor try to deceive this policeman, so that even target domain features can go through this classification layer very well. Okay, so because of this ordeal, because of this difficulty, I try to make very similar features as far as I'm from the same categories. In the viewpoint of discriminator, my goal is to distinguish them. So I do my job. I do my best for my job. So I just do my backpropagation. But here, if we do backpropagation according to the discriminator, my features will be different according to the domains. So my backpropagation gradient is changed, reversed. Okay, so that the without reverse gradient reverse, my features will be different according to the domain. But because of this reversal, my features will be very similarly generated. That is the main idea of GRL. Okay, and that is just a pretty popularly used domain adaptation, unsupervised domain adaptation scheme. After that, in 2018, new one that is very similar to the previous one. Only one difference is the classifier. So they use the same discriminator using reversed gradient, so called GRL. But instead of using this kind of classifier, they use some kind of a comparison. Okay, so comparison with prototypes. Now, so classifier is replaced by the comparison with set of prototypes. So that is very similar to previous one. That's why this is the most important. Only classification is replaced by comparison. So it compares with prototypes. So with this updated comparison classifier, they insist that the performance is better than original one. Okay, so comparison rather than classification. Again, the next one is also very fun, interesting. Keep by adversarial training, we have to always memorize that. By adversarial training, we mean there is some ordeal, some difficulty. Then, because of that ordeal, we change our features. Okay. So their main idea is, their main observation is previous ones, they are more focused on just aligning. So for example, before adaptation, the source domain in blue and target domain in red. When our code in the previous days, our code is always just aligning. Okay, so this is boundary obtained in the source domain. Since we just focused on aligning, after aligned, we observe that some samples are not correctly classified, okay, trained in the source domain, because we only concerned about alignment. We didn't care about good classification. So what is proposed is they modified classifier into two different classifiers by using some kind of dropout. So you make some nodes with you put some nodes value 0, right? That is dropout. So by using different dropout, the original classifier is modified into two different classifiers. Okay, so by using this loss function, what we can do is the black one solid line is original classification boundary obtained from original source domain train, but by the classifier C1, we have this dotted boundary, and by classifier C2, we have this different boundary. Because of this dropout, we have different classifiers, and our loss function shows that their difference is maximized because of this minus sign. Difference method, that means classifier work just very differently. So we have classification boundary here and here. That means we have ordeal, right? Because without these two different classifier, we have only one classifier. Then even though we have some small number of failure case, it was okay. So there is no big ordeal, big difficulty. But now, since we have very tight boundaries, upper side and lower side, so we have some difficult. Many samples fails in this case. So because of this ordeal, the generator try his best to have new features which are more located far away from the boundaries, original boundary. So again, because of this ordeal, because of this difficulty generated from C1 and C2, oh, from the generator viewpoint, oh, I have to generate my features more differently. The feature should be more far away from the classification boundary. So the generator tried to generate better features. Okay, so in the feature space, different feature means different locations, right? In this feature visualization. So this is a new features generated by G. Why? Because we have this ordeal. Wow, because of the different very sensitive classifiers, I may fail in for many samples. So I have to move some samples up and other samples down. That is the goal. So always, whenever we have some difficulty to make final result better, we mean we are using adversarial scheme. Okay. So same authors. Okay, the ICLR and then followed by CBPR by same authors. In this case, the basic idea is same as previous one, but instead of using two different classifier modification using dropout, they just equipped me with installed with real different classifiers, as you can see here. So not using dropout, they just set the different classifiers. That is same. So because of those different classifiers, okay, their classifier make discrepancy maximized. That means they also put ordeal. Okay, again, in this case, left side, the shaded regions are just a fair case, okay, because of those boundaries. but we make things more worse. That means the boundary is moved. Okay, so make things more vague. Okay, so now from the viewpoint of generator, wow, the situation became worse and worse. So I have to try my best to fit in the correct side. So I have to generate better features. That is called minimizing discrepancy. So my features are more well located. We keep doing it. So finally, even in this very the weird boundaries, very hard. It is ordeal. Wow, these are very severe situation. But even in this situation, my features are well classified. Okay, so my generator, because of ordeal, my generator can produce appropriate the features. Okay, so it's fun, right? Because of two different very sensitive classifiers, in order to satisfy both classifiers, finally I have to generate the features in this location and in this location. Okay, so you know ordeal, right? Ordeal, that is difficulty, hardship, right? Because of this hard situation, my generator do my best to relocate. That means the more to generate different features. Okay, the features differently. That is how we do domain adaptation using or how we do domain alignment using adversarial scheme. Okay. So using adversarial scheme, okay, the discriminator is my ordeal. This is my difficulty, okay? And also, two different classifiers are my ordeal because they made a classification boundary very difficultly, right? Very hard. Made a situation very hard to satisfy this boundary and this boundary. My feature should be more separated, right? That is this adversarial scheme. And now we have different classifiers equipped, and we try to generate uh, features very separate. Okay, again, because of this ordeal, this is ordeal, this is the difficulty, hardship given. Because of this hardship, I do my best. That is adversarial training. This is so far we talked about feature distribution alignment. Okay, our goal is to align two different domains, different distributions. Now we also think about appearance by converting appearance from two different domains. We try to do so it's not feature alignment. We try to align looks, but actually we change our looks so that the two looks to be very similar. That means features are aligned, of course, right? So we don't treat the features directly. We treat the pixel values. Okay, then when they are similarly looked, then that means features are also aligned. That's our basic idea. So this approach uses an auxiliary reconstruction task to create a shared representation for each of the domains. So this network is called DRCN. this DRCN tries to solve these two tasks simultaneously. The first one is, of course, classification of source data. So classification of source data should be done very well, of course. And also, we try to reconstruct the unlabeled target data. So that should be reconstructed very correctly. So it should be very similar to original, of course. This makes sure that the network learns not only to discriminate correctly, but also preserve original information about the target data. Because the reconstruction is correctly done, that means original one's identity, original one's information is well preserved. Okay, so by using both scheme simultaneously, so in this paper, the authors claim that the reconstruction pipeline learns to transform source images into images that resemble the target data set. So because of this, the both sides resembles, and also classification is done very well. So they suggest, they claim that common representation is learned for both. So again, source data is well trained with label data, and target domain samples are well trained so that they are reconstructed very well. By reconstructed very well, we mean their original identity is well preserved, but at the same time, they are well they in the middle of these two processes, the features are well aligned. They expect. And the other one, second one, image to image based domain adaptation is like change is to change the looks, the two different domain images changes so that they are very similar. They look very similar. It is thanks to the development of GAN. Okay, GAN. Thanks to GAN, we can change style. We can change image look. Okay, so if the target domain, source domain images are all different, then we can just change the image look so that they look very similar. Then automatically we can expect the features are also aligned because their looks are very similar. So they just trained so that source domain image is mapped into some shared space. Okay, even they also learn, they can get back to original, and they figure out, okay, in this embedding space, I can map and I can get back. Also from target domain, I can go to some embedding space and I can go back. And they do once more. I can move to the embedding space to even to different domain. I can get back. Okay, it is thanks to cyclic GAN. You know, in the cyclic GAN, we do just to go to some other space, and then we go back, right, to make sure my mapping is working very well, because when I go somewhere and when I come back, my look is same as original, then my mapping is done correctly, I can sure. So for example, from source domain, I make a travel to the embedding space to the target domain. When I came back, my look is very same as original. Then my mapping functions are working very well. So using such image to image translation in this embedding space, we can assure that our looks in this virtual space, we are together, we are same, we are very similar. Okay, then that will guarantee features are well aligned. So using this kind of cyclic consistency, they made a test like A is domain, source domain, while B is target domain. So in the source domain, they trained, and so illumination is different, right? Very different. So C shows that without domain adaptation for the task B, the bottom one, the test result is very uncomfortable. But with domain adaptation, the result is almost the same as ground truth. So they show that using their proposed image-to-image translation for domain adaptation, they were successful. Okay, they showed that. And before we close the unsupervised domain adaptation, just this one shows the output from my lab using unsupervised domain adaptation applied to object detection and applied to semantic segmentation. Very shortly speaking for this one, our basic goal is to generate a feature that is robust to domain change, right? So for source domain, target domain, our goal is to generate very similar features. In our case, thanks to the development of GAN technology, we use some cyclic GAN. So not only source domain and target domain, we also generate the middle domain pictures. So our goal is to generate the feature that is compatible with source domain, not only source domain, target domain, but also generated domains. So that means we believe that our generated features are more robust to domain shift, because we can deal with many other domains as well in the training stage. So our features will be very robust. This one, we also make some augmentation so that target and source domains are mixed well. Okay, that was used for semantic segmentation. Okay, so far the time goes very fast, and I think many of you are already very tired. But I think as far as you pretty understood the previous ones, that's good enough. Okay, just already we mentioned the main idea of domain adaptation, and I showed the adversarial schemes in domain adaptation. I think that's good enough. But I make the semi-unsupervised domain adaptation very quickly. Okay, so I'll go very quickly from now on. And just to remind again, okay, recall labeled, we always source domain, we have labeled data. In target domain, we have a different. So in semi-supervised domain adaptation, we have a few number of labeled data and bunch of unlabeled data. By few number, we mean just only 1 or 3 labeled data in each category. Okay, and also you can also refer to the difference with just the conventional semi-supervised learning. Okay, so here labeled okay data are just more than 10 categories. Okay, 10 shot. Okay, and that category just in one category, just labeled data 1 or 3 here, labeled data in one category about 10. Okay. And since we already studied fusion learning, actually, you know, fusion learning is also supervised learning, right? That is supervised learning. Even though in the test stage, we have a few number of the labels and data, that is supervised learning. So we can compare with this fusion learning with supervised DA. So in domain adaptation, our goal is to adapt to new domain. Okay, so learn from the other domain. We have a knowledge from other domain. We try to adapt the knowledge to new domain. In fusion learning, we try to adapt to new tasks or new categories. Okay, So categories are all different. They are unseen in the training stage. But given new categories, how to adapt our knowledge to new categories, that is fusion learning. How to adapt our knowledge to new domain, that is domain adaptation. Okay, this is I have two slides with this mark. One is in the adversarial domain adaptation slide. The other is this. So two are just really important slides. Okay, here in the semi-supervised domain adaptation, the most popularly referred method is min-max entropy based SSDA. Okay, so in order to understand the min-max entropy, I prepared this, so it will be really helpful. We have two samples with different probabilities. So those probabilities are same. In example 2, they are different. Example 3, the probabilities are very different. In terms of entropy, H is entropy. Entropy is defined, calculated as probability and log probability. And when they are equal, very similar, entropy is maximized, right? So when we say entropy is very high, which means the samples are very vague, very ambiguous. We don't know which one is very highly likely. That is when entropy maximized case. And when we have very small entropy, that means we have entropy minimized case. That means very clear. One is dominating, right? That is entropy minimized. So again, even though we saw this one, by softmax, this is a logit vector in the CNN layer final stage. It is reformed using a softmax function. That means the bigger one get more bigger, others get smaller. Okay, so that makes we have a hard max. We may think of a hard max. What is hard max? That is to make the biggest one alive, while others are all zero. That is hard max. But in our CNN deep learning case, we also respect some other cases. So we just suppress, not making them all zero, just suppress. But the winner makes the biggest one. That is softmax. But if you apply entropy maximization, they try to make everyone similar, the probability similar. Why? Because when we have same probability, entropy is maximized. Okay, so when we say entropy maximized, that means situation is vague, ambiguous. I don't know which one is better or worse. So everything is just ambiguous. That is entropy maximized. So here, if we just think about the labeled case only, where blue one is labeled source and the red one is labeled target in category 1 and class 2. Okay, so we don't think about the unlabeled case here. Then when you just make a supervised learning after training, you will observe that the features are were gathered in each category and were separated between categories. Okay, so they are a little spread, but here after training, they are more aggregated. Okay, that is a good thing without thinking about unlabeled data. But in semi-supervised learning, our goal is to use unlabeled data, right? So in order to get unlabeled data included in our process, we apply entropy maximization to the prototype. By prototype, we mean just among blue ones, centroid vector is prototype. That's a representative vector that is prototype. To make a situation vague, okay, we apply entropy maximization. Okay, thanks to entropy maximization, prototype is moved into this side. Okay, so compared to original situation and new situation, what changed? Now they are clearly separated, but they become together, right? So they are closer after entropy maximization. So they are less distinguishable, right? So situation is similar, right? Everything seems same, right? So entropy maximization will give you this one. So entropy maximization on the prototypes, their location will be very closer. And second one, for the remaining ones, we apply entropy minimization. So by entropy minimization, we want to make things clear, right? So similar one get closer and different one get apart. Okay, so after entropy minimization, now we get this kind of grouping, including unlabeled data. But if you are interested in domain adaptation, especially in semi-supervised domain adaptation, this is the starting point, because the following papers are all based on min-max entropy-based SSDA, or they are always referring to this one. So you have to understand this one. Okay, so entropy maximization on prototype will relocate the prototypes to the front end. Okay, things get unclear because now they are very far away, but things are very clear. But now, because of entropy maximization, they become closer. So things are unclear. Okay, they are about to be mixed, right? Unclear. And then fixing the prototype, they apply entropy minimization. By entropy minimization, we mean things should be clear. So the labeled data as well as unlabeled data get closer each other, and they are well separated between classes and well grouped in each category. Okay, I hope you fully understood min max entropy. Okay, and I want to finish with the result from my lab here. So last year, ECCB 2020, we observed that in the case of semi-supervised learning, because of unlabeled data, when we have some kind of alignment, like using supervised learning for the labeled data only, then in the target domain, labeled data are well grouped with source domain labeled data, but still we have the unlabeled data, which are very separated from the labeled data, or there's a few unlabeled data. So they have some intra-domain discrepancy. So in order to reduce not only inter-domain discrepancy, of course, but also intra-domain discrepancy, we just have three modules. One is attraction, perturbation, and exploration. So by attraction, we mean using MMD, which was introduced in the previous slide. By attraction using MMD, we try to make distributions aligned, right? So the labeled source domain data and labeled target domain data, and also unlabeled target domain data, their distribution should be minimized using MMD. So maybe we call it attraction. even though they are separated, we expect that they are pretty aligned. That is attraction. But after attraction, we can see so many of them are not yet moved enough. Okay, so we use very similar approach used in minimax entropy. Okay, minimax entropy. For the prototypes, we apply entropy maximization. So the prototype is moved to unclear region. Okay, so from the safe region, which is the center of my labeled data, now it is relocated to some uncertain region because of entropy maximization. Okay, and that is called the perturb. Okay, after and also thanks to following entropy minimization applied to features. Okay, your features are also try to follow your updated prototype. Okay, so again, it is to it is to mix isolated unlabeled data. By perturbing your prototype, we want to make them all together. Okay, and after perturbation, we can of course observe that still there are some unlabeled data far away, but some are nearby with my labeled data. Then we apply pseudo labels, okay, to unlabeled data, pseudo labels. So we have more labeled data now. So we keep doing attraction, perturbation, and exploration. We keep training these three modules. Then we were able to get very good results. As you can see, ours shows the best performance according to our test. So that is how our algorithm was successfully applied. Okay, for semi-supervised domain adaptation. Okay, I want to finish with this one. I just want to say that SSDA was successfully applied for not only for classification, but also for semantic segmentation and for object detection. Okay, but we observe there are a few number of SSDA related paper yet. That means there's a big room for us to attack because it is a pretty new area compared to unsupervised domain adaptation. Unsupervised domain adaptation, we feel like it's kind of, it seems like a red ocean already. There are large number of papers, but in the case of semi-supervised domain adaptation, still we have a bunch of large rooms for us. So you can think about if you are interested in domain adaptation, you better think about semi-supervised domain adaptation. Thank you for your attention. I think you are very tired now. I'm sorry for this long lecture. Okay, and we can have a Q&A session now.
Okay, thank you very much, Professor Kim. It's a very in-depth lecture, and maybe it's a little bit difficult for us to follow. But
I'm sorry.
yeah, but that's a good introduction for us to extend our research. Then, okay. Okay, is there any question from audience?
And fusion learning and SSDA, whatever you have a question, it's okay to have this one, or later on you can ask to send your question to Adi. Everyone
Yes.
knows Adi?
Yes, yes.
Okay,
yes.
then he can just transfer it okay, to me. Okay.
Yeah, get big applause to Professor Kim again. And okay,
Thank you, thank you. Thank you
Yes.
for your invitation. It was great for me.
Oke. Gimana Adi, mau difoto dulu apa?
Okay, thank you everyone for joining the lecture. And as Professor Kim has said, if you have any question about future learning or maybe about the domain adaptation, please feel free to email me and I will forward the question to Professor Kim. Yeah, to close the session, we would like to have a virtual photo session. So everyone, please turn on the camera. We can. Please wait a minute.
Anytime.
Excuse me, Professor Kim. Could you please turn off the share screen?
Which screen? Finishing my screen. You want me to finish my screen? Like this? Or what?
Yeah. So we can have the gallery view. Okay. Yep. Thank you, everyone. So I think we are good. Thanks for joining the call. Thank you again for Professor Kim for joining the lecture. We hope that we can invite you again in another time in the future. Thank you, everyone.
Okay, thank
And
you.
I'm looking forward to seeing Adi soon. Okay.
Okay.